This lecture is about field theories for non-Fermi liquids. So I will briefly, before we talk about non-Fermi liquid, I will briefly review Fermi liquids in the introduction, and then discuss two different types of non-Fermi liquids, one with so-called hot Fermi surface, the other with hot spots, and then talk about both perturbative and non-perturbative approaches to these systems. So in condensed matter physics, we want to capture universal long-distance physics using effective theories. And the effective theory is not only a useful computational tool, but it's very useful in classifying different states of quantum matter. And different states have different number of low energy degrees freedom, and the form of low energy effective theories differ greatly. So if you have a trivial insulator, then there's no low energy degrees freedom below the gap. And if you have a topological state, then you can have some low energy degrees freedom, but they usually scale sub-extensively in the system size. For example, if you have a ground state degeneracy, then the number of low energy degrees freedom doesn't scale with the system size L. And if you have a, say, gapless boundary state, then low energy degrees freedom scales with the system size L to the power smaller than the space dimension. And if you have a gapless propagating degrees freedom in the bulk, for example, in relativistic quantum field theory, as we heard in the previous talk, then entropy density scales with temperature to the power space dimension. But now, if in metallic states, as Liang mentioned in the morning, the size of the Fermi surface, Kf, enters as a scale, and that is a scale that basically governs the number of gapless mode in your system. So as far as temperature dependence is concerned, the system behaves like a one-dimensional system. And then it's as if number of one-dimensional gapless degrees freedom increases as the system size increases. So for this reason, the effective theories for systems with Fermi surface are usually formulated in terms of quantum field theory that include continuously many gapless degrees freedom, okay? Where the continuous flavor corresponds to the angle around the Fermi surface. Okay, that's one way to think about the problem. And this lecture is about low energy theories for non-Fermi liquids that arise near quantum critical points. So before we talk about non-Fermi liquid, let's start with non-interacting fermion. And we all know that it can be diagonalized using single particle basis. And many body eigenstates are labeled by occupation number of single particle state. So in a sense, the shape of the occupied region, so Fermi surface, is a good quantum number when there is no interaction. Now, if we turn on interaction, then particles can exchange momentum and scatter from one momentum point to another momentum points, and that cause quantum fluctuations of the Fermi surface. So naively, one would think that this Fermi surface will fluctuate at a time scale dictated by the microscopic interaction strength, and then you may think that Fermi surface there will be no sharp Fermi surface at all. That's the naive expectation. But Landau, and later more systematically in RG language by Shankar and Polchinski, taught us that this is not the case. And it turns out that even when there's a strong interaction, as far as the interaction is short-ranged, the Fermi surface remains well-defined. The reason is that the lifetime of excitation created very close to the Fermi surface is very long. So for example, if I have a particle with energy E created above the Fermi surface, and we can ask how long it takes for that state to decay into different many-body state, such as the one with one additional particle Hall excitation through that two-body interaction. And then you can compute the, say, inverse of the lifetime to the leading order, say, in perturbation. And it should be proportional to the square of the interaction strength. And it turns out that actually it goes to 0 in the limit that energy of the single particle goes to 0 in a quadratic way. The reason is that in order for that particle to scatter into other state, it has to stay above the Fermi C within the shell with energy window E. And suppose that energy is E1. And then at the same time, you create a hole with energy E2. I remove electron at energy minus E2, so hole with energy E2, and particle with energy E3. And then the sum of those energy E1, E2, E3 should be the original energy E, and then phase space. And there are 3 variables, and then the phase space that obey that constraint goes as E square because there's only one energy conservation. And that limited phase space give rise to long lifetime of particle created close to the Fermi surface. That means although the microscopic time scale with the interaction is very short, as you go to low energy, the Fermi surface is actually essentially rigid. It doesn't fluctuate much. And for example, this manifests itself as a sharp peak in the spectral function. So if you create a particle with fixed momentum k close to Fermi surface, and you ask what is the probability for that particle to have energy omega, that's the spectral function. And because of the interaction, because of this quantum fluctuation, it no longer has a delta function peak. It has some broadening, but the width of the broadening goes to 0 as E square, which is much smaller compared to energy itself of the quasi-particle. So because of that, even in the presence of rather strong interaction, the single particle excitations are well defined, and many-body eigenstate at low energy are still labeled by occupation number of those single particle state. And this is quite remarkable statement that one wouldn't expect naively. And because of that, many properties of interacting Fermi liquid are qualitatively similar to those of free fermion. Okay? Now, this so-called quasi-particle picture break down in different ways, and we heard one way in the morning from Liang. And here I will be talking about non-Fermi liquids that arise near quantum phase transition. So there are different materials, but the basic idea is that if you tune some parameters of the Hamiltonian, it can be doping or pressure or magnetic field, non-thermal parameter at 0 temperature, then your ground state may undergo a quantum phase transition at 0 temperature. And if the quantum phase transition is a continuous transition, then at the critical point, the order parameter associated with the broken symmetry become gapless. And because of that additional gapless mode, electrons interact more strongly compared to Fermi liquid, and that's where non-Fermi liquid states are usually realized, seen. And experimentally, people often characterize non-Fermi liquid in terms of anomalous temperature dependencies in thermodynamic quantities and transport properties. from theoretical point of view, spectroscopic quantity like spectral functions are more direct probe, but they are harder to measure experimentally. So there are far fewer spectroscopic evidences in those materials. So what happens at quantum critical point is that, as I mentioned, if there is some spontaneous symmetry breaking on one side of the phase diagram, and if you tune the system to the critical point, then at the critical point, the order parameter have a long range, has an infinite correlation length. Although there is no symmetry breaking, it is still dynamically fluctuating, and it has infinite correlation length, and that can and those fluctuating order parameters can mediate long-range interactions between electrons. And long-range interactions in real space corresponds to singular interaction in momentum or energy space. And although there is still limited phase space that goes down as a E square, if the interaction vertex is strongly energy dependent in the small energy limit, then that can enhance non-forward scattering, the momentum changing scattering of electrons, and that can destroy coherent quasi-particle. Okay, so this is the rough idea. So the theories for those non-Fermi liquid states are interacting field theories that cannot be diagonalized in single particle basis. Okay, so in a sense, more genuine form of interacting field theories. So this.
That tau is a single particle relaxation time. Right?
Yeah, just lifetime.
Right, but then why in a non-forward scattering? I mean, just
This
particle can relax just through like small angle scattering, right? Right. So by non-forward, you mean that the momentum has to change a lot?
Oh, it doesn't have to change a lot, but it cannot stay at the same momentum, right? It's a small but non-forward. Yeah. Yeah, this is not transport relaxation. It's just the single particle relaxation. Okay, so the main topic of this lecture is about understanding field theories for those non-Fermi liquid state. So two important factors that determines the nature of non-Fermi liquid that arise near quantum critical points are, not surprisingly, space dimension and the wave vector associated with a broken symmetry. We are talking about quantum phase transition, and then on the order side, there will be some, you can have a Q equals 0 order that is associated with breaking of some internal symmetry at uniform order. That is Q equals 0 order. But you may also have some kind of density wave, spin density or charge density wave transition. Then you have a non-zero Q vector. So that's this wave vector of the ordering. So first, space dimension. So in 3 space dimension, as we know, quantum fluctuations are not that strong at low energies. Usually, for many field theories, 3 + 1 space-time dimension is the upper critical dimension, where the quantum correction is only logarithmic. So there is some deviation from Fermi liquid behavior, but it's not that strong. As you go to lower dimension, of course, quantum fluctuation becomes stronger at IR, say in 1D. Even even in the presence of short-range interaction, you don't have Fermi liquid state. But in 1 dimension, unlike higher dimension, you have only Fermi points. So there's no qualitative difference between matter with from other critical, bosonic critical system, for example. That's why bosonization works so well there. So for this reason, 2 space dimension is perhaps the most interesting dimension. It's low enough that quantum fluctuation become very strong in the IR, but it's high enough that it supports infinitely many Gapliss mode in the low energy. So therefore, we will mainly focus on two space dimension in this lecture. And then the second factor is the wave vector for associated with the spontaneous symmetry breaking. And then at the critical point, the collective mode becomes soft at that wave vector because it is that wave vector where the order parameter condenses on the ordered side, right? So for Q equals 0 case is when the spontaneous symmetry breaking is some internal symmetry. It doesn't have to be internal symmetry. It can be some space symmetry, but it can break the spatial rotational symmetry. So that is the nematic phase transition. Or it can break the spin rotational symmetry, some magnetic transition at Q equals 0, for example. So there, the collective mode is gapless at Q equals 0. And as a result, almost everywhere on the Fermi surface, this electron can absorb and emit this collective mode while staying close to the Fermi surface, because you can always find the direction tangential to the Fermi surface. And because of that, almost everywhere on the Fermi surface, electron lose the quasi-particle is destroyed. And this is what we call hot Fermi surface. On the other hand, if the collective mode carries finite non-zero momentum, like if you have some spin density wave transition as some pi momentum, then that is the momentum at which the collective mode become gapless at the critical point. And then if you are sitting somewhere at a genetic point on the Fermi surface, then this fermion when that fermion absorb or emit the gapless collective mode, generically it is scattered away from the Fermi surface. So therefore, those fermions at genetic point do not strongly couple with those collective mode at low energy. And there are only discrete set of so-called hotspots connected by the Q vector. And there, this electron can scatter from Fermi surface to another point on the Fermi surface, stay at low energy, while emitting or absorbing this gapless collective mode. So in that case, we expect that the coupling between those electrons near the hotspot remains strong at low energy. Okay? So these are two different types of non-Fermi liquid.
So what about the role of conserved charges, conserved quantities?
Yeah, that also matters. And then what is whether it's a different channel, whether it's a spin or a charge, and what is the global symmetry. But it seems that they are less important.
So you would say the ferromagnetic and the nematic cases are quite similar?
Yeah, at the kinematic level, they are similar. Dynamically, of course, they can be different, but the kinematic structure is pretty similar. Yeah. Yes.
How long is the Q?
Sorry?
How long is the Q?
Q is either 0 or non-zero. So, so it can be, Q is the inverse length scale of the density wave. Okay, so it can be order of 1 over lattice spacing. That can be as large as it can be. Or if you have a uniform order, then it is 0. But 0 is qualitatively different from anything that is non-zero. I think that's what I'm trying to say.
Sorry. So how does this argument work if the system has Fermi line instead of Fermi surface?
Oh, you mean if you have a line of line node, Fermi arc embedded in? Yeah. Okay. I will get to that point later. Yeah. I will get to that point. This is an important question.
So the way you define hotspots, can they be extended?
So, okay, so maybe, so if you have a, say, 3-dimensional matter, if you have a 2-dimensional Fermi surface in 3 dimensions, and then if you have some density wave transition there, then hotspot become hot line, right? Because there will be linear manifold on the Fermi surface connected by the Q vector. So in that case, you will have to consider hot line theory. instead of hotspot theory. Yeah. But if you have a line node in 3 dimension, then the hotspot theory is okay. So the dimension of Fermi surface is also important. Yeah, that's a good. Yeah, okay, so that requires fine tuning. Yeah, that's a whole different class. So if you have a perfect nesting, then it's basically 1D like. But here I will consider a genetic 2D system where the Fermi surface has a non-zero curvature and maybe globally convex. So whenever the local curvature changes sign, that's another type of Lipschitz transition where the density of state for some particle channel diverges around that point. So here I'm considering a genetic case. Okay, so let's first consider hot Fermi surface. So here I'm going to use this Ising-nematic quantum critical point as an example. Okay. So what is Ising-nematic phase transition? So imagine you have some microscopic system that has some discrete rotation symmetry, say 4-fold rotation symmetry. Then in a metal, and then as you tune some interaction strengths, your system may undergo quantum phase transition that breaks the, say, 4-fold rotation symmetry spontaneously into, say, 2-fold symmetry. So that is the nematic transition. So in terms of the shape of the Fermi surface, in the symmetric case, your Fermi surface will be symmetric under 90-degree rotation, but in the ordered phase, in the broken symmetry phase, you can break the symmetry in 2 of the principal directions, so your Fermi surface can be elongated either horizontally or vertically. And then you can introduce Ising order parameter, whose sign determines the deformation of the Fermi surface. Okay? So this is a well-defined quantum phase transition where the discrete rotation symmetry is spontaneously broken. And here we are interested in this critical point. Okay? So at the critical point, we not only have gapless electronic degrees freedom at low energies, but you also have gapless fluctuating order parameter. So here is effective action. So the first line is just the kinetic energy of electron. I'm working in 2 + 1 dimensions. So d3k is sum over frequency and spatial momentum. And E of k includes all the information about the band structure. And then the second line is the, say, Ginzburg-Landau action for Ising order parameter written in frequency and momentum space. And then most importantly, you have a coupling between fluctuating order parameter and electron. So to understand this form of the coupling, let's imagine first we are in the ordered phase. In the ordered phase, you may turn on some negative mass square term for the boson that, yes?
A very, very quick question. The C on the second line, that's not the electron creation operator, right?
So sorry, this is the velocity of the collective mode, which is in general different from velocity of fermion. Thank you. So to understand this form of the coupling, oh, sorry.
Why you do not include fermion-fermion interactions?
Yeah, so there are quartic interaction for fermion and boson as well. Yeah.
That's the ellipsis.
So suppose we are in the ordered phase where the order parameter is condensed at q equals 0, say it's positive. Then expectation value of this guy is 0 at q equals 0. then in that case, this last term behaves like a k-dependent chemical potential for electron, right? It's diagonal in momentum space. And then the sign of that k-dependent chemical potential depends on the direction around the Fermi surface. So when phi has a positive expectation value, then this term is positive in the horizontal direction and negative along the vertical direction, right? Because of this sign structure. That means electrons are depleted along the horizontal direction and they are more populated in the vertical direction. So that describes the Fermi surface that is elongated along the vertical direction. Then when phi is opposite, then it's the other way around. That's in the ordered phase. Now at the critical point, you no longer have a non-zero expectation value, but this phi still can fluctuate, not only at q equals 0, but or at any momentum. Okay? And then when this collective mode carries non-zero momentum, then it is no longer diagonal for electron. So electron also need to change the momentum to conserve the total momentum. So basically, electron can scatter from momentum k to k plus q by observing collective mode with momentum q. That's the fermion-boson vortex. And although the full theory should include all the gapless mode on the Fermi surface, it turns out that in order to understand properties that are local in momentum space, such as the electron spectral function at a given momentum, you can actually consider only a patch, some local region in the momentum space. And that is due to the emergent locality in momentum space. So this is the story. Suppose I am focusing on very low energy. So let's impose some energy cutoff lambda, which is much, much smaller than the Fermi energy. Then low energy electrons are mainly located within the thin shell near the Fermi surface, right? And suppose I have some electron here, and I want to know the bosoning mode that can couple with this low energy fermion. So because I'm at low energy, this electron, after say observing some bosoning mode, it needs to stay close to the Fermi surface, right? So as a result, this electron cannot scatter too far in the vertical direction. So the momentum of the boson that couples to this fermion varies only up to lambda in the vertical direction, right? On the other hand, if this boson carries momentum in this tangential direction to the Fermi surface, the boson can carry much larger momentum, okay? Because energy increases only quadratically in this direction as opposed to linear increase in this vertical direction. As a result, this fermion near this region are mainly coupled with a boson whose momentum is defined within this long bar. The right-hand panel is the momentum space for the boson, okay? And then the width of the bar is order of lambda, whereas the length of the bar is much larger. It's the square root of lambda times kf, the size of the Fermi surface. That has to do with the curvature of the Fermi surface, okay? So electrons here are mainly coupled with the boson in this momentum. And then if you look at electrons, say, at different angle around that red region, that electrons are mainly coupled with the boson in this kinematic region, okay? So you see, although the blue bar and red bar has some overlap near the center, the region of overlapped region goes to 0 as a lambda square as you go to low energy limit. So therefore, in the low energy limit, most of the scattering happens within this bar, and this overlap region can be ignored. So that results in the decoupling of the electron here with at different angle. Okay, although these electrons are coupled with the same boson, there's only one boson. These bosons are separated in the momentum space. They are kinematically separated. So these electrons are talking to boson in this region, and these electrons are talking to in this region. And as you go to low energy, the boson do not talk to each other at different momentum. That's the picture. As a result, in order to understand the properties that are local in momentum space, you can just focus on some local region in the Fermi surface. So this is the so-called patch theory. Okay? Of course, this no longer holds when you include, say, 4 fermion interaction that can scatter fermion from any point to any other point. And that becomes important when you include superconductivity. Okay? So that's an important caveat in this patch theory. So in order to understand superconductivity, you have to go beyond the superconductivity. But here, I'm mainly interested in understanding the normal state above the superconducting transition where pairing interaction is, 4 fermion pairing interaction is not strong. So that's the scope of this setup for now.
Does it still apply when you have a magnetic field?
Sorry?
Does this locality still apply when you have a magnetic field?
If you have an external magnetic field.
Yes. A weak magnetic field.
That become that you know if you have just Zeeman coupling, that this is whole. But if you have a orbital coupling, then it become more complicated.
In what way does it become?
Because in some gauge you break the spatial translational invariance. So maybe there's some gauge invariant notion of emergent momentum locality, but that is not manifest in a fixed gauge. So this is the say okay. Before we move there, so if I want to say understand the property of electron in this region, I have to include the electron in this patch of the Fermi surface and the bosoning mode within this bar. But also there's an antipodal point where the Fermi surface is tangential to that part, right? So that's why it's 2 patch theory, not 1 patch theory. So generically in 2 dimension, you have 2 patches that are coupled with a boson in the same kinematic region. Okay? So 2 patch theory includes a fermionic excitation at the 2 antipodal points and the collective mode. So now we can say focus on the patch centered at 1 momentum, say in the x direction. Then now you can expand your momentum away from this point, this little case, a deviation from this center of the patch, and then locally dispersion in the perpendicular direction, energy increases linearly, and then in the vertical direction, it increases quadratically. That's the local shape of the Fermi surface. And then everything else is pretty much similar. Here, S plus or minus represent these 2 patches, okay? The sign of the Fermi velocity in the, say, x direction. Yes?
So why do you only consider these 2 angles? And like maybe in the previous slide, like you have only...
Yeah, you have to, in general, you have to consider all angle.
This is just an...
Yeah, but suppose I want to know spectral function of fermion around this point. Then for that purpose, I can use this patch theory. If you want to know the property of fermion at this angle, then you need this patch theory. So the whole theory is kind of given by sum of infinitely many patch theories. Okay, and then similar to what we heard from Liang in the morning, you can do the scaling analysis. You can lower the energy and momentum such that the kinetic energy of fermion and boson remains scale invariant. And under such scale transformation, you immediately find that the coupling between electron and boson grows as you go to low energy. So it's so-called relevant coupling. So as you go to IR, the interaction become more and more important. So one needs some small parameter to control your calculation. Okay.
So in the fermion saturation
Yes, yeah.
And
So the dispersion deep inside the Fermi surface is not really relevant. What matter is the shape of the Fermi surface near the Fermi surface.
okay.
Yeah.
So it's okay.
Yeah. So as far as you have a Fermi surface that is convex everywhere, this is the right patch theory. But if you have some inflection point, then you have to change the form of the patch theory. Right? So in general, you have a Fermi surface with inflection point. Then in general, that theory, the total system is given by patch theory with a different dispersion. So then as a result, the universal, so thermodynamic properties given by sum of different patch theory. So that is one of the examples where you have more than one dynamical exponent, dynamical critical exponent in one system, for example.
So in this, if I just look at these two patch theories, the boson fields only give you scattering within each patch. Is that correct?
Yeah, because you know,
Small momentum.
yeah, because to create momentum with large momentum is the energy penalty for that.
Right, and it's almost like density. If I rewrite it in real space, just take this two patch theory. It's like the boson and fermion density. Well, I guess it's order parameter and density actually.
Yes, that's right. Yeah, yeah.
So if you think about long range, so if I think about near critical boson but not completely critical boson, right? Then I think about this framework of RG. So I should start with the full Fermi surface, and in the intermediate region I can deal with this patch theory. But as the length scale goes longer than the interaction or the correlation, I should go back to the full Fermi surface lots of times.
Well, you always have the full Fermi surface, right? But just the scaling changes. There's some crossover from the scaling dictated by this critical theory to the Fermi liquid scaling at low energy. Yeah.
So the index J, that index J
Yeah.
represent for patch for different angles.
No, sorry. So this J is just a generalized spin flavor. So original model, I have a spin up and down, but here I've written some general version of N flavor. So this is purely internal flavor. And then this is only for one patch. And then the full theory includes all other patch, which is not written here. 3?
So I remember there were some non-analytic corrections to when you go away from just two patches and take the full Fermi surface, you get non-analytic corrections even in Fermi liquid theory or even in this class of theories. So does that ultimately not matter as you go?
So, right. So the hope, which is not proven here yet, is that the universal properties of low energy fermion does not depend on the size of the Fermi surface in a singular way. It's pretty much like the local property that Liang mentioned. So although there's a entire Fermi surface, if I look at the spectral function at a given momentum, that property doesn't care about the shape and size of other part of the Fermi surface. If that's the case, then patch theory is valid. If not, then you should go back to the full theory.
Okay. Because those non-analytic corrections do something much more dangerous. They might even break the...
So non-analytic in
For instance, take the nematic case, right? You had a Q square term in the kinetic term for the boson. You could get a non-analytic correction that looks like Q, for instance. And that changes the theory completely. The nature of the second.
right. So the figuring out what is the universal non-analytic form of that self-energy is part of the goal, right?
But only for all three photoparameters.
Pardon?
Only for all three photoparameters.
Oh, not for the...
No,
I
not
see.
Fuji2.
But what about large N? Then you have some SUN.
SUN, yeah. But if the field is scalar, no, sorry, if the field is scalar, the field is we don't have that.
To all orders.
So I worried about first order transition in the say ferromagnetic case.
Yeah.
Yeah. So yeah, one has to be careful that this phase transition itself is a continuous transition.
that mean under RG flow, this S cannot get renormalized because the curvature or the radius of the
Right. So okay, this is also a good question. So in the non-Fermi liquid, so of course the total number of total charge is of course microscopically conserved, right? And then within this patch theory, the number of fermion within the patch is also conserved. So it's as if number of fermion at each patch is conserved. So they are emergent conserved quantity. But they are not strictly conserved because if you have two patches, these two patches can talk to each other near the boundary.
Right.
So therefore, there is still some leak. The fermion can scatter out of the patch and can scatter into the patch, right? So as a result, the conservation, the emergent conservation is weaker than the infinite U1 conservation in Fermi liquid. For example, in Fermi liquid at low energy, the quasi-particle number is conserved at every point in momentum space on the Fermi surface. That's the infinitely many conserved quantity. In non-Fermi liquid, you don't have such U1 to the infinite. But still, there's an approximate sense of approximately conserved quantity. So one way to say that is say the number of particles within each patch, the divergence of that is non-zero, but it goes to zero as you go to low energy. But it goes to zero at a slower rate than in Fermi liquid. That's perhaps another way of characterizing non-Fermi liquid. I don't know.
Okay, just a quick question. So in this two-patch theory, the fermion dispersion is anisotropic in the x and y direction.
Yes.
The boson dispersion is isotropic. So how do we do the scaling?
Where, okay, so here, although the bare dispersion is isotropic, the renormalized boson that couples to this part of the Fermi surface is anisotropic. But you have to remember the full theory still has a C4 symmetry.
Okay, let's just talk about two-patch theory.
Yeah.
Then you're saying that essentially in the end when I do the scaling, the x and y direction are different.
Yeah, they become different. Renormalized dispersion become different.
Fermion multiply the fermion dispersion.
Fermion is anisotropic from the beginning, right?
Yeah.
And also boson.
Boson then acquires
Yeah,
boson,
yeah.
goes with the fermion.
That's
not
right.
the other way around.
That's right, yeah. Dimitri?
I just wanted to make a connection to Ashford-Mervin types of physics. So the first two lines of the action would well describe coupling to of fermions to regular acoustic phonons, right?
Mm-hmm.
You have linear dispersion to the bosons and the Fermi surface. But in this case, we know the coupling would be irrelevant, right? Soft energy would go
Right.
as at the peak of the frequency. So the very important assumption here is that coupling to the bosonic field is of the non-trivial components. You would have a factor of Q in there, and that would bring the soft energy down.
That's right, yeah. Yeah. Okay, so any other question? Okay, so if not, now let's move on to perturbative approaches. So the perturbative approaches that I'm going to review in the following, say, 15 minutes can be applied both Q equals 0 and Q equals non-zero case, but I will just explain in the context of Q equals 0 theory here. Okay. So perhaps most benign deformation, so the theory is in 2+1 dimension flows to strong coupling theory in 2+1 dimension, which we don't know, and we don't know what to do with it. So the goal is to deform the theory such that it's not that different from the original theory, but still we can understand the quantum physics in a controlled way, right? And then one of an expansion is to expand the number of fermion flavor, vector flavor, from say spin 2 to n flavor. Okay, so maybe this is most benign deformation. So the hope is that if you have a large number of fermions flavor, then this collective mode can have many channels to decay, right? So as a result, the collective mode is very strongly damped in the large N limit. And then the feedback of the collective mode to the fermion will become weaker because fluctuations of the boson is suppressed in the large N limit. So that is the idea. And this idea has worked quite well, say in relativistic field theory, say ON vector model. We know how to compute, say, critical exponents perturbatively in 1/n. However, this is not the case in the presence of Fermi surface, and then the reason is that there are so many gapless mode on the Fermi surface that some scattering processes are strongly enhanced because fermions can, for example, if you have this kind of high order vortex correction, right, between this boson and fermion, naive 1/n counting give you very big suppression for this kind of processes. But it turns out that this fermion, as it goes through many interactions, it can stay very close to the Fermi surface. And as a result, the infrared singularity can be enhanced such that this high order vortex correction is as important as the leading order vortex correction. Okay? And then here I'm not explaining any detail, but it turns out that the theory with a vector N flavor behaves more like a matrix model that we just heard in the previous talk. So in the large N limit, if you have just one patch, then it turns out that all planar diagrams that you have to sum over in, say, large N Yang-Mills theory that we heard before are important to the leading order in 1/n. And then if you have two-patch theory, there are even larger set of diagrams that one has to include. So the large N non-Fermi liquid theory still remains an open problem. Okay, we don't know what is the nature of the theory in the large N limit.
What about the one patch case?
The one patch case is understood. Yeah. Just briefly. So one patch theory, you still have to sum over all planar diagram, but you can still compute the exponents non-perturbatively there. Okay, so people have come up with different ideas. So one is change the dynamics of the bosons. For example, the Ising order parameter has a q-square dispersion in space momentum, but one may change the exponent to a smaller power. Then the energy of the boson increases more steeply as a function of q at low energy, and that reduces the density of state for the bosonic degrees freedom, and that suppresses quantum fluctuation. And then one can use that parameter, say epsilon, as a small parameter. This scheme has advantage that it manifestly keeps all the symmetry of the original system. But one downside of this scheme is that it breaks the locality. As soon as this power becomes fractional number, this is no longer local kinetic term. It kind of describes non-local, say, hopping in real space. Technically, what this means is that with this non-local kinetic term, the system cannot have, the boson cannot have a non-trivial anomalous dimension. So for example, suppose the real propagator of the boson has some power where eta represents anomalous dimension, right? The correction to this, okay? And then we usually want to compute this perturbatively in epsilon. But then this anomalous dimension in the perturbative scheme can usually arises a logarithmic correction, but the low correction diverges both in IR and UV, right? So lambda is some UV cutoff and Q is some small momentum IR cutoff. And then you end up having this kind of UV divergent correction that is non-local in space. But this kind of correction cannot appear in local RG scheme because UV divergent contribution come from short distance fluctuation. So they are bound to be local. So you cannot have this kind of quantum correction that gives rise to anomalous dimension. So if you have a system that have non-trivial anomalous dimension, then this scheme is problematic. And then one can think about dimensional regularization. We can change the dimension. But in the presence of Fermi surface, there's no unique way of changing the dimension because you have not only the dimension of space, which is denoted as D, but also you can change the dimension of Fermi surface. Here I denote as M. Okay? So the original target theory is here. It's a one-dimensional Fermi surface embedded in two dimension, right? And then this is strongly coupled theory, and then to approach the theory, you can start from different direction. Okay? This is the non-uniqueness. And the most straightforward dimensional regularization is going in this diagonal direction, where you change the space dimension and the dimension of the Fermi surface, keeping the codimension of Fermi surface to be 1. Right? Codimension is D minus M. Right? So if you go to the diagonal direction, for example, then at this point you have a two-dimensional Fermi surface in 3 dimensions. That's the usual metallic state in 3 dimensions, right? And then you may hope to access this point starting from this point by using deviation from that point as a small parameter. This has some nice property. For example, it keeps the finite density of state. But one downside of this method is so-called UV-IR mixing. So the emergent locality in momentum space that I explained before is true only when the dimension of the Fermi surface is 1. And as soon as dimension of the Fermi surface become greater than 1, then in order to understand even the local property in the momentum space, you require to know the entire Fermi surface. For example, at this point, you have a 2-dimensional Fermi surface in 3-dimensional space, right? And then suppose I want to know, say, I understand this, say, vortex correction where fermion at this momentum scatter to nearby point on the Fermi surface. But this process, say if this is Q, then it can couple with other particle excitation with minus Q. But in the presence of 2-dimensional Fermi surface, there are infinitely many points on the Fermi surface that can be connected by momentum minus Q, right? So therefore, this particle excitation ends up coupling with all these particle excitation, low energy particle excitation that are extended around the Fermi surface. So as a result, the size of the Fermi surface, Kf, enters as a scale even for the local properties in momentum space. For example, if you look at say, some spectral function, for example, at one point in the momentum as a function of frequency, it not only has some universal scale exponent, but also it depends on the ratio between frequency and the size of the Fermi surface. And then the main problem is that when when the Fermi surface dimension is not 1, whenever it's greater than 1, this parameter enters as a important ratio. So physically, in this theory, in the original target theory, you want to understand the case where this argument is 1. That's when m is 1, right? But if you start from here and then take the low energy limit first, then you have a power that is greater than 1, and then you take the low energy limit, and this is 0. And then usually this function f as a function of that ratio is a singular function in the small x limit. So therefore, the low energy limit do not commute with m goes to 1 limit. Okay, so this and then one method that avoid this UV-IR mixing is to tune the codimension of the Fermi surface. So now you go vertically. Because you have a UV-IR mixing for m greater than 1, you don't want to go this region, so you move vertically. So you can now keep the dimension of the Fermi surface to be 1, and then change the embedding dimension of space. Okay? For example, if you go vertically, that point represents the line node embedded in three-dimensional space. For example, this can be realized if you have a two-dimensional usual Fermi surface in 3 dimension, and then turn on, say, p-wave pairing. Then that gaps out the electron away from the xy plane, and then you can have a line node in the xy plane. Okay, and then you can consider, say, quantum phase transition within this semi-metallic state, right? You can have a nematic quantum phase transition within the semi-metallic state, and you can ask what is the property of the quantum critical point within the semi-metal. And then you can continuously connect these two theories. So this is the target theory. This is the semi-metal with the line node. And you can tune this parameter while keeping the locality of the theory. And in this case, it turns out that the upper critical dimension is 5½ namely the coupling between boson and fermion become marginal in 5½ space dimension. And then you can use the deviation away from this as a small parameter. And then yeah, you can find in this scheme you can find the fixed point. So this is just some examples of physical observable that are computed in this dimensional regularization scheme. So let me just give some comment here. So for some kinematic region, it turns out that the collective mode doesn't acquire non-trivial anomalous dimension up to some loop order.
So this is still based on a patch theory, or
This is still patch theory. Yeah, yeah.
Two patch theory or one patch?
Two patch theory. Yeah, yeah.
I think we need to end soon.
Okay. Yeah. Okay. So I will stop after this. Okay. So so I guess one nice thing about this is that near the upper critical dimension, because of the fermionic density of state vanishes at 0 energy, there is no superconducting instability. So near the upper critical dimension, you don't have to worry about pairing instability. And indeed, the four fermion interaction is irrelevant. Of course, that changes as you approach the 2 dimension. Then you expect the superconducting instability to set in. But then another comment is that this has been puzzling, but somehow the boson, the collective mode, doesn't receive non-trivial anomalous dimension up to some loop order. People have checked up to 3 loop order, but there's no reason for symmetry that protect the scaling dimension of boson, and it's likely that even at higher order loop, there will be some non-trivial anomalous dimension. Okay, so this is just a summary of different perturbative scheme, and I would say there's no perfect scheme. I mean, each scheme has its own pros and cons. But personally, I like to think that maybe it's better to keep the locality to study the universal dynamics.
Yeah, so they will try to change by changing the dispersion of the fermion part of the theory to make the control, or
To make it non-analytic, as
yeah,
we.
Right. For example, you have k minus k1 minus k2 squared. You didn't want to change those exponents just to make it control.
No, people haven't tried. Yeah. Yeah.
So I know that the quantum free property of fermion coupling with boson inclusion is really important question, and so you have developed a kind of a field theoretical method to calculate lava coupling through the previous boson. So I'm just curious about whether your result can somehow compare with the Cauchy terminal, or maybe just even the Laplace module. I asked it partially because I
Yeah, so maybe I will comment on the comparison with the, say, recent numerical study in the second part of my talk.